Okay, it's me again. And our second work is integrating AI cluster into virtual private cloud. Let me first introduce the background. Uh, in the large AI cluster, the network is mainly separated into two parts. The first one is the front end. The front end network connects the GPU servers to VPCs using DPU. It is a powerful NICs thanks to its embedded CPU, and it provides hundreds of gigabits per second bandwidth. And the other part of the AI cluster is the backend network. It mainly connects the GPU nodes. It uses commodity NICs, also known as ASIC NICs. The ASIC NICs cannot hold or execute the full VPC policy engine, but each GPU has a, a commodity NIC connecting it. So the number of the commodity NICs in a GPU node is typically 4 or 8. So the bandwidth of the backend network are the terabit scale bandwidth. So the it resulting the performance lives on one side and the VPC semantics lives on the other side. This separation become a serious problem for data intensive AI workloads. For example, a GPU server may have 400 gigabits backend NICs, providing an aggregate backend bandwidth of 3.2 terabits per second. And the front-end DPU just provide 200 gigabits per second. So this represents a 16 times bandwidth mismatch. This problem appears in several important workloads. The first one is recommendation models. Recommendation models continuously retrieve training samples and embedding from cloud storage. Multimodal training consumes large image and video datasets that may be pre-processed by VPC virtual machines. Federated learning requires frequent parameter exchange, while long context inference can generate substantial KV cache retrieval traffic. In each case, data transfer through the front-end DPU can fall behind the GPU computation. As a result, expensive GPUs remain idle while waiting for the data from VPC. As a result, we want to connect the backend network to the VPC so that GPUs can get the VPC data from backend network. From backend network. However, the backend NICs have insufficient compute, memory, and programmability for a full vSwitch. And if we use the host CPU for vSwitch, it will consume tenant resources and violates bare metal isolation. So to address the problem, our key idea is to decouple complex policy lookup from high-speed packet forwarding. Instead of putting the complete VPC rule database and policy engine on every backend NIC, we move global rule lookup to a controller. The controller stores the VPC rule tables, and the NIC only stores the match action entries required by current active flows. Common case packets can therefore remain on the hardware fast path. Let me briefly explain the packet processing workflow in our architecture. When a packet enters the NIC, the NIC checks firstly checks its hardware flow table. If there is a miss, an immediate agent will send the flows 5 tuple to the controller. Then the controller makes a table lookup and resolves VPC rules. Then the controller configures fast path and writes a match action entry to the NIC's flow table. Then the packets can forward via fast path. After that, subsequent packets belonging to the same flow are forwarded directly in hardware. Therefore, only the first packet normally enters the slow path. Steady state traffic bypasses the controller. The slow path is mainly limited to flow misses, policy updates, and the cleanup of inactive entries. The physical location of the controller affects both performance and reliability. So we consider 3 deployment options. The first option is to run the controller on the host CPU. It is convenient, but as I said, it will consume talent resources and it violates bare metal isolation. The second option is to use it at remote server CPU. It is isolated and resilient, but it may increase latency as the control flow may be hybrid with the data flow. The third one is front-end DPU arm. It can be low latency local control as it has a dedicated network path. But a local DPU failure can affect downstream NICs, as in a GPU server, it's usually only have one DPU in the front end and have many backend NICs in the backend. So we design a hybrid strategy. That is, we make local DPU control in the common case, and if there is a failure, we will switch it to the remote controller. We first evaluated the potential performance improvement using analytical simulation. With the 200 gigabits front-end DPU, loading 512 megabytes data takes 25.6 milliseconds. It reduces modeled GPU utilization to about 11.7%. With the unified 3.2 terabits backend path, the loading time falls to 1.6 milliseconds. The GPU utilization approaches 100% and end-to-end throughput improves by 8 times. And the main performance cost of our design is the additional latency experienced by the first packet of a flow. To measure this cost, we repeatedly generated flow table misses on a DPU-enabled NIC. A controller running on the host CPU generated the corresponding rules and installed them on the NIC. This measured extra latency was 71.17 microseconds at P999. This result suggests that when the controller is located nearby, first packet processing can remain within 10 of microseconds. However, the P999 latency reached 266.84 microseconds. This long-tail behavior remains an important concern for production deployment, which needs further improvement. To conclude, we propose a VPC Fusion backend architecture for AI clusters. The central principle is simple: keep complex VPC intelligence away from the packet hot path. The controller performs global policy lookup while command Linux maintain only the active forwarding states required by current flows. Our evaluation shows near full GPU utilization in the analytical model, an 8 times modeled throughput improvement, and only 71.17 microseconds measured P999 rule installation latency. In the future, we will propose production validation and study controller scaling and making stateful network functions. That's all. Thank you.
Okay, so thanks for the presentation. It's a very practical system. Okay, so are there any questions from the audience? Okay. Thank you for your presentation. Have you considered using the GPU for the backend network? Would that make the design similar?
Okay. Using DPU in the backend. Yes.
Yes.
I think it's a wonderful idea, but the DPU is too expensive. If we use DPU in the backend, it will cost a lot. And the DPU has an operation system in it. So if we change the backend to the DPUs, we need to maintain the operating system. It increases the complexity of our maintenance work. That's
Okay, thank you.
okay.
Yeah, can you elaborate a bit more on this architecture, right? So
Yeah.
you only that you can fit front end, right? Not back end or scale out. So is that what you try to do?
Yes.
Can you give a bit more justification on this? Yeah, the reason why follow what he just asked, right? So what if you use GPU in DPU, right? Scale up network.
If we use DPU in the backend, we can make the V switch in the DPU ARM core. So we did not to decouple policy lookup from forwarding. We can just make the whole V switch in the DPU core. So it is very easy if we change the backend NICs to DPUs. However, it is too expensive and complex, so we don't use the DPU.
But it's okay. We
Mm.
can talk offline.
Okay.
I have another quick question. So,
Yeah.
do you have any ideas on how to solve the first packet latency? Because it's in the real pain to the deployment, right? Any ideas on how to, potential ideas on how to solve this problem?
Yeah, we consider a lot about the first packet latency, but it is hard to address this problem, and our initial thought is to get information from what we are doing, and we can pre-processed. So this can
Then you need some caching, right?
yes.
Set up some connection in advance, so the packet will be in the faster path.
Yes, yes.
It's based on the prediction on the like applications behavior.
Yeah.
Do some caching, right?
Yes, yes.
Great.
In our future work, we will try to solve it.
Okay, so that's a very great talk. Okay, so
Yeah.
let's thank Yinhe Wang. Okay.
Okay. Thank you.
Thank you.